Although our two-opt algorithm is very simple, in fact, it is not always the best solution when we solve large problems, because this is a greedy algorithm. And then normally greedy algorithm has its limitations, and then it usually gives us a local optimum solution, which may be far from the global optimum solution. For example, this can be easily understood from a one-dimensional function. Let's see, we have a function like this. From our observation, we can tell this is so-called our global optimum. However, let's see, if we start at an initial point here, our small step, typically we call it a local search. Our two-opt operation, swapping two edges in the entire TSP tour, is a local search operation. In a one-dimensional function, our local search can be a small shift in either way, on the left side or on the right side, in the left direction or on the right direction. So here, if we only move a small step, and then this point will be jumped to this point, we see an improvement on the cost function, and then further jump down, and then jump down to a local optimum solution. If we have a local search on either left-hand side or on the right-hand side, and then the total cost will increase no matter which direction you go. So to conquer the local optimum barrier, sometimes we need to provide slight chances that the point can jump outside of this local minimum, even jump twice, and then to finally get our global optimum solutions. So one of the representative method here to allow the local search jumping outside local optimum and then have a chance to find a global optimum solution is we call simulate annealing. So the simulate annealing, sometimes we abbreviate into the SA, is an analogy of a physics process. Items of some objects, let's see iron, will gradually reduce their temperature and then form some certain shape. So at first, the cell in the metal will keep shaking in the neighborhood because this is a high temperature. Then after it is cooling down, the cell gradually reduces this movement. Finally, the atom will not move at all. And then this is our low temperature case. So the entire process from high temperature to low temperature, this is we call annealing. So introducing this concept in our algorithm indicates that at first when the temperature is high, the movement of the atom are very random. So we allow a high chance that the solution jump outside from local minimum to some solution which is worse. So this one we allow the jump. And then after the temperature gradually reduces, finally we want to yield a good solution, at least guarantee that it is a local optimum. So this, after the temperature goes down, the solution kind of converges. So in short, at first we try to randomly change the solution even it is not improved using our greedy algorithm. And then finally we reduce the chance that the solution jump outside of a local optimum, and then finally we expect that after several jumps, the solution can be better than the first optimum solution from any initial point. So mathematically, we will have our SA-based two-opt algorithm. So every time we want to do our swapping, we will calculate the cost difference from our any pair A, B, C, D minus the new pair AC, BD. This is our change of the cost or the change of the distance. So without simulated annealing, the algorithm will do our swapping if and only if our cost is improved. But then under the concept of simulated annealing, that means even if our swap operation does not reduce the cost, and then there is a chance that the cost is greater or equal to 0. Then there are still small chance that we can accept these swap operations to allow it to jump outside of a local minimum. So the probability that we allow it to be jumped is calculated based on the temperature. So let's see, we have the Bernoulli distribution, and then the probability for the Bernoulli distribution we accept is given by the exponential of the cost difference divided by the temperature T. So the physical meaning here is simple. When the T value is high, means the temperature is high. Under this case, the high temperature give a relatively large probability. So you have a higher chance that you accept the jump. And then when the temperature is low, and then our probability will reduces and finally reduce to 0. That means as the temperature goes smaller and smaller, definitely this is a positive temperature in our context, and then our probability to accept the change becomes to 0. In particular, we will typically update our temperature based on a constant factor. Every time we do one step or one swap operations, we will adjust our temperature and gradually reduce it by a factor alpha.